Hear me? Yes, you can. OK, so let's start right off with an example. Let's say you're keeping track of the balance in your bank account, and you want to implement a function for withdrawing an amount X. More or less, this is the code you could write. First, you would check whether the balance is enough to support the withdrawal, and if so, you would update it with the remaining amount. Right? And this is a fine piece of code in a sequential setting, but not in a concurrent one. In particular, you can run into trouble when you have two versions of this running in parallel. You can see this with a simple example. Let's say we start with a balance of 8, and you try to withdraw 5 on each side. You can have an execution that first checks whether the balance is enough on the left. The test goes through. You make the same test on the right. It goes through again, and then you proceed with withdrawing 5 on each side, ending up with a negative balance. Right? And this is clearly something that should not happen. So this is a kind of bugs that arise in concurrency because we have no control over the scheduler, so we don't control the order in which certain instructions are executed in different threads. So now if you think of one of the first ways of testing whether a program is correct, it's just by giving it some input and see whether you get the right output, right? Unfortunately, in concurrency, even in this simplistic setting of fixed inputs, testing does not work so well. So because you don't control the scheduler, still under fixed input, you have an exponentially large set of possible executions or traces or interleavings that come out of different scheduling choices. Right? So when you run your program, you get pretty much an arbitrary point in this space. You look into it, it doesn't have a bug. You realize you might have been lucky, so you repeat the process. You get another arbitrary point. It's not a bug. So you repeat this process 100 times. Now you're confident that your program is correct, where in fact there is a small neighborhood up here of buggy traces that you failed to discover just by testing. Right? So there is a line of work in this setting called predictive techniques, which try to lift testing to concurrency. The idea is that you again start with an arbitrary point in this space, but now we're going to look into this interleaving and reason about alternative interleavings that could have taken place, thereby concluding that not just this particular observed interleaving is correct, but in fact the whole neighborhood around it. Right? So now we repeat this process a few times, and at some point we discover this non-empty intersection here, which means that we have managed to predict a bug, even though we didn't observe one, out of these executions we got out of our testing. Right? So in this talk, I'm interested in bugs as data races. A data race is a concurrent access to a shared resource where at least one access modifies the resource. In this case, we have two threads. They both act as concurrently a shared variable x. One of them writes to x. This is a data race, so we want to be able to detect this kind of behavior. In the predictive world, this means that we want to be able to detect this not by analyzing a program, but rather by analyzing another trace. Right? So this is what we get out of our testing phase. It's a data race free trace. But in fact, if you look into it, you'll find out that certain other reorderings can take place, which in fact will lead to another trace that will expose the data race. So there's a long body of work on this topic, and very interesting papers coming out in the recent years. Most of the existing literature focuses on fast heuristics. So the idea is that you develop polynomial time algorithms which typically have one-sided errors. So they're either unsound, so they might report a data race when there is none, or they're incomplete, meaning that they might miss some races. Right now, since we're in a testing loop, incompleteness is typically OK, because you still stand some chances of discovering your data race in a future iteration. So really, most of the techniques are polynomial time sound techniques that are incomplete. So they might miss a few races, and in fact, they typically miss even simpler races. Right? So this work tries to push the boundaries further with regards to this incompleteness. So what we develop is a new algorithm for dynamic data race prediction. We call it M2. In alignment to existing literature, this is a polynomial time sound algorithm, which is also complete when it comes to traces that only consist of two threads. When you go beyond two threads, the algorithm might have false negatives. And to mitigate this problem, we're also developing some criteria for over-approximating this set of false negatives, which means that the algorithm can draw your attention to the part of the input for which it is uncertain. And finally, we have some interesting experiments which show that the algorithm has a potential. So to be a bit more concrete, let me make my problem statement clear. So the input to the data race prediction problem is a concurrent trace. It consists of a number of threads. They communicate over shared memory, so they can either write to it or read from it. And they synchronize over locks. For simplicity, I'm going to assume that the number of threads and the number of memory locations is constant. Now, the trace defines an observation function, which is a map from reads to writes. So every read is mapped to the write that is observed under sequential consistency semantics. And moreover, we have a conflicting pair of events. These are two events that access the same memory location, and one of them at least is modifying it, is writing to it. Right. And now we want to find out whether this conflicting pair is a predictable data race of our input trace T, meaning that we can create a witness trace T star, which is just a reordering of certain events of T. So T star executes every prefix locally of its thread up to some point. Moreover, every read in T star sees the same write as in T, and the two events over which we're testing for a race appear at the end, manifesting the data race. Right. So we insist that this requirement holds, so the two observation functions agree. The reason is that if you guarantee this, then you know that the behavior exposed by this T star is actually behavior that is exhibited by the concurrent program, so the race report is a sound report. Right. Now, back to literature, most of these techniques, at least the ones that I'm aware of, are partial order-based heuristics. The idea is that you build a partial order over the events of your input trace, and you report that E1 and E2 are in race if they're unordered by this partial order. Right. Now, unfortunately, virtually all such approaches miss simple races like the one shown in this figure, where we have a data race between WX and RX exposed by the witness trace here. And the reason why this happens is that if you look under the hood, the partial order that is constructed typically is one which forces this ordering. So this release is ordered before the acquired down here. And the reason why this happens is because the two critical sections here contain conflicting events, these two writes on variable y. Reasoning about reordering conflicting events is typically computationally expensive. So in order to avoid an expensive computation, the heuristics just try to order these conflicting events in the same way as in the input trace. On the other hand, you can see that, in fact, if you want to expose this data race, you need to swap these two critical sections, and you need to swap these two conflicting events, and these ones down here as well. So since we're interested into catching this kind of data races, we have to be constructing partial orders which allow, at least in some cases, to not order pairs of conflicting events. Right? So we want to construct partial orders which are more relaxed than what is out there in the literature. Right? Now, because we are doing this now, a linearization of our partial order might be one in which has an observation function that is not in agreement to the observation function of the input trace. So we associate, with this modeling, the realizability problem of a partial order, which is given a partial order, find a linearization T star of it, which not only linearizes the partial order, but also gives the same observation function as the one you had in your input trace. Right? So existing heuristics more or less guarantee this. In our case, we're constructing more relaxed partial orders, so this is no longer guaranteed. Right? But this is the key technical problem that you need to solve in order to do data race prediction efficiently. So our first step in addressing this challenge is defining something called closed partial orders. So a partial order is closed if two conditions are met. The first condition says that for every read, if there is a conflicting write event that is ordered before the read, then you must also order it before the observation of the read. Right? And the symmetric case here says that if the observation of the read is ordered before the conflicting write, then the read itself must also be ordered before the conflicting write. Right? And the second condition is in order to respect critical sections and lock semantics. The idea is that if you have two critical sections on the same lock, and the acquire of the first is ordered before the release of the second, then the release of the first must be ordered before the acquire of the second. Right? Now, a partial order might be closed or not. What we know is that if the partial order is realizable, then there is a unique minimal strengthening of the partial order that takes it to a closed partial order. And we call this strengthening the closure of the initial partial order. Right? The next step then that we need to be able to perform in order to solve our initial problem is compute this closure, compute this minimal strengthening that will guarantee that these three rules will hold. Right? And the question is, how fast can you do this? Now, conceptually, what happens here is that these rules say that if certain events are ordered, then new orderings must also be inserted in the partial order in order to guarantee that you don't violate any of these rules. So again, on the technical level, the way I am picturing this is that you need to solve a problem regarding maintaining incrementally a partial order. And by this, I mean that you need to be able to support two operations. You need to be able to insert new orderings. Right? And then you need to be able to query about the ordering of two events, taking into account all the preceding updates. Right? Now, how can you solve this? There are classically two ways you can go about it. Typically, we represent partial orders as graphs. On the one end, you can treat each update operation by simply inserting an edge in this graph. And when you're presented with a query operation, you need to traverse this graph and recover all the orderings that have been formed transitively through the updates. Now, updates are fast. They cost constant time, but query costs you graph traversal, which is linear time. On the other end, you can take an update operation and directly compute the transitive closure. It will take at least linear time, and then queries come essentially for free. Now, in our setting, we're dealing with really huge traces where n can be of the order of 10 to the 8. So spending linear time in either extreme is really not desirable. It's not going to scale well. So the way we're solving this, in the paper, we're solving this challenge by developing a data structure which can actually maintain incrementally a partial order by only spending logarithmic time per either operation. Right? And this is a complexity that is much more suitable for dealing with so large inputs. Fine, so we can use now this data structure to compute the closure of a partial order. And this is an operation that can be performed in amortized logarithmic time per edge insertion that you're making, so per strengthening that you're making in your partial order. This computation can have two outcomes. On the one end, you might end up with some cyclic orderings. In this case, you know that the closure does not exist. And moreover, the partial order that you started with is not realizable. So you can't linearize it and also respect the observation function. On the other hand, you might successfully complete the closure without encountering a cycle. In this case, you have a closed partial order which may or may not be realizable. You don't know that yet, right? So the next step in this process is try to identify some additional conditions under which, once you reach this point, you can guarantee that your partial order is realizable, right? And without going into too many details, these conditions are phrased in something we call a max-min theorem, which essentially says that if you take a partial order over an event set x, if you, moreover, can partition x into two sets, x1 and x2, where x1 is totally ordered and x2 orders all pairs of conflicting events, then you're guaranteed that your initial partial order is in fact realizable, right? Notice that we still allow pairs of conflicting events to not be ordered as long as they sit on opposite sets. So on x1 and x2, these two events are unordered. Now, this is the second building block of the algorithm. Without going into further details, I just want to give you the algorithm as in high level. When we're given a trace T and a conflicting pair of events over which we want to test whether it constitutes a predictable data race, the algorithm initially constructs a partial order where these two events are maximal. They appear down here. Moreover, every read is preceded by its observation, so this blue edge up here. And if you have an acquire event that opens a critical section that doesn't close, then every release event on the same lock must be ordered before it. So again, pictures better than words. This acquire here is opening a critical section that never closes, so the release down here must be ordered before the acquire. Right. Now, the second step is to compute the closure of this partial order. So notice here that this This observation up here, this write, is ordered before a conflicting write here, so the closure will in fact strengthen this partial order with this ordering. The read must also precede this conflicting write. At this point, we have a closed partial order. We still don't know whether it's realizable. At this point, the algorithm will make some heuristic steps. It will non-deterministically choose some thread I and will partition the set of events into two sets. Yi is going to contain all the events of thread I, and Y not I is going to contain all the other events. And now the non-deterministic choice happens in this loop where we iterate over pairs of events that are conflicting and belong to the set Y not I, and we're going to order them in the same way as in the input trace. So we're still relying on the input trace to guess certain orderings between conflicting events, but not all of them, right? And in this example, this is shown by the green edge here. So these are two conflicting events on the Y not I set, which are unordered. So we're going to guess the ordering and close the partial order again. Right? And we will perform this up to a point where no two conflicting events in Y not I are unordered. And at this point, we're satisfying the conditions of the max-min theorem. Yi is a totally ordered set. Y not I, after this loop has been executed, is ordering all pairs of conflicting events. So the max-min theorem guarantees that this partial order is realizable, so we can construct a witness trace in the end. Right? So two more remarks in this algorithm. The first is that, well, as I said earlier, all the non-determinism happens here. When you only have two threads, every pair of events that fall into Y not I will actually belong to the same trace, to the same thread. So they will already be ordered, which means that you have to make no guesses about additional orderings here. So the algorithm will never enter this phase. Now, the algorithm will reject a data race only if a cycle is formed in the partial order sometime along in this process, right? So this will never happen down here when you only have two threads, which means that the algorithm will also make complete reports of data races. And when it comes to more than two threads, again, we can over-approximate the set of false negatives by taking in that set only the event pairs which were rejected after the algorithm executed these lines. Right. So this is as far as theory is taking us. Now I will jump into some experiments. We have a prototype implementation of this algorithm together with some algorithmic engineering and optimizations that I'm not going to dive into. We have compared it again against a few other works. HB is a standard. Standard happens before technique, and these three came out fairly recently. We have our benchmark set. Every benchmark here contributes a single trace. And now here you can see how many data races are predicted by each of these methods. Our algorithm here is predicting more data races. And in fact, when we use this criteria to over-approximate a set of false negatives, we find that this set is empty in each case. So we have actually found all data races in this data set. So I will conclude here. This paper is about a new algorithm for predicting data races. It's a polynomial time and fast algorithm. It makes sound reports of data races. It's also complete when it comes to threads. And we have some extra criteria for detecting completeness dynamically, together with some interesting experiments. Thank you. I'm happy to take questions.
Thank you. Questions?
Thanks very much. So I assume you're assuming sequential consistency. Would your approach generalize to weaker memory models as well?
So with some confidence, I can say that these techniques can be lifted to TSO and PSO. It's not immediate. There's still some technicalities that I didn't go into, which I'm not sure they would be straightforwardly solved for those models, but I think you can do it. I don't know about other models.
Oh, another question. Oh, hi, great talk. In your comparison, you show the
results from each algorithm, could you also comment on how long time it takes for each algorithm to produce these results?
Yeah, I have some numbers here. Yeah, so I have some numbers here. Maybe you want to focus on the total times down here. So the algorithm takes more time than existing techniques, but not terribly longer. There is some algorithmic engineering involved, though, so it's not so straightforward to make it efficient.
Any further question? I had a question on the data structure. So you mentioned you had a data structure for implementing the partial orders.
Yeah.
So what is the basis for this data structure? Is it like union find, or what's in there?
Not really. I guess yeah, we're here. So what you want to do essentially in graph theoretic world is maintain incrementally the transitive closure of a DAG. And the key underlying data structure that I borrow from that literature is basically something called Fenwick trees, which are used to compute incremental suffix minima and maxima. You can use those data structures together with some algorithms on top to develop the one that we're using here.
Very short? Okay, very short last question.
Does this generalize to handle atomic read-write instructions pretty naturally?
I don't know, so maybe, yeah.
Okay, let's thank Andreas again.